Let's record. Minimum and maximum. The chapter is called Application of Derivatives. Application of Derivatives. And then chapter 1, that is 2.1, maximum and minimum. 2.1, sorry about that. I think it stops doing it with time, hopefully. This disco thing. Let's learn how to use first derivative test and then general derivatives to find maximum minimum of the functions. So, a function given a function f of x, a function f of x. This is what we need to remember. If f prime, the derivative at the point, is negative, then f of x, so that's the important thing. You have a graph representing the profit of your selling socks on Amazon. There's a graph. In January, you sold this amount, then it's a little bit, because people needed socks, then summer heat, less socks were sold. If the derivative over here, that is your derivative slope, is negative, that means the original function is decreasing. So the profit is decreasing at that particular moment. For example, day or months, whatever your A is. That's how you know, oh, people don't like my socks anymore, maybe because it's summer. And you can guess if derivative is positive, so you're checking what is happening here in January, then that means f of x is the original function increasing at a. So basically the derivative, which you remember is synonym derivative rate of change, how fast something is changing, instantaneous rate of change. Maybe some of you here are electromagnetic and you just messing up. How fast something is changing and so on. This means that, oh, if it's positive, the original function is increasing, negative, decreasing. Let me restart, maybe it will help. Like so. Now, in general, at the point or at the interval. But what is happening if it's 0? Let's see 0. If the derivative at a did not help 0, then f of x is neither decreasing nor increasing. That's what I told you. Oh, the floor. How steep the floor is, 0 steep. Or the constant, derivative of the constant is 0. So f of x is a constant. There is a constant. Makes sense. So your profit, for example, looks like so. You still have some profit, but it's constant. Yesterday you sold 5 socks, tomorrow you sold 5 socks. In 2 days you also sold 5 socks. Derivative will be 0. So there's no change. Nothing good, nothing bad. That is very nice and very important to understand. And I will show you soon how to memorize it better. Relative, minimum, and maximum. I usually say min, max. We say that f of x is a relative maximum. Let me put it in red or pink. Relative max. Relative max means local of y equals f of x if there exists an open interval I. Do you know what open means? It means with brackets at the end, with braces at the end, A, B. So it doesn't include endpoints. containing C in the domain are all possible inputs of F such that that's a very nice abbreviation, F of C, so if it's a relative maximum or local maximum, then it means at that point function is greater than everyone else around it for all x in I. That does not make sense at all, so I will show you the picture. The picture means here is x-axis and y-axis on some kind of interval from A to B, and I is a very nice notation for the interval, because I interval, there's a C located somewhere there, not necessarily in the middle, just C, somewhere over here. At that C, you have a little hill. So the graph of the function looks like so. There may be more hills, but this hill is called local or relative maximum. So let's put also a synonym here, local. We also call it sometimes local extreme values, local relative, local maximum, local minimum. So local. Locally, it's a hill. Second one, vice versa, F. So was it F of C? Nope. Can you please fix? This should be F of C. F of C. Yeah. F of C. So it's like so. F of C. At C, F of C is your local hill of the hike. Same thing. F of C is called a relative, relative or local. Local, you will see it in the literature as local because it's literally local. Minimum. If there exists such an interval containing C's, such that, same thing, but now F of C should be less than outputs around it on that interval I. So on the picture above, I'll go like so, and I will show you that this point over here in the interval is called local minimum or relative minimum, while this one was local maximum or relative maximum. Relative means relatively to other points. So it might be not the biggest hill or not the smallest valley, but locally or relatively to the points around it, it is a hill and a pit, yeah, or valley. It stopped. Oh, you see, with time it stops. Interesting. Nice. So, this is the idea. Let's find it. Let's learn how to find it and what is going on there. And then also learn how to work with graphs and derivatives. So here is the graph and the function example. The function name is y equals 1/3 x cubed minus x plus 2/3. You are now professional in differentiating because you passed the first exam. So now we are very happy that you know how to take derivatives. Very nice. So, local, I'll be saying local, relative and local is the same thing, but local is faster to write, so I like it more. Local maximum of the function, so it is, let's see, over here, let's say it's -1, and the height is, we need to figure out where is the height. Local maximum is x equals -1, f of x actually have to be calculated. So let's figure it out. 1/3 minus 1 cubed minus negative 1 plus 2/3 equals, well, I'll wait for you, maybe you know. What do you think? Who's good with fractions? Who got 4/3? 4/3. This is local maximum, relative maximum. You will also see in the literature they call it local extreme value. That is also this extreme term, they like using it in English. Minimum. Local minimum is, let me put it in purple color. Seems like, so as you can see, there are some points lower over here on the left, but this guy definitely is local minimum. For example, it's at number 1. How do I know? Because in this neighborhood, this is the lowest height, right? Same with the maximum. At this neighborhood, f of minus 1 was the highest point. Later, as you can see, it was higher than that. So what? Locally, it was a mountain. Locally, there is a pit. Local minimum. Local minimum. That is ugly. Local minimum. So let's find it. I claim that this is x equals 1. Let's find the height. F of 1. This was actually f of minus 1. F of 1 is 1/3, 1 to the third, minus 1 plus 2/3. The height of that local minimum is 0. Thank you. So I'll put in the box, and you can see it from the graph, it is 0. So this, if you're hiking this, you kind of should understand. Oh, I'm hiking up. This is my mountain number 1. Now I'm going down. This is my pit number 1. And maybe there will be mountain number 2 and then one more pit. And maybe there will be more of them. So that's exactly how mountains look like. You will have lots of local maximums and local minimums, which are called relative extreme values. Now, how about increasing, decreasing definitions we just looked through? Let's practice answering these questions. That is going to the test. We always like testing that you understand where the function is increasing and where the function is decreasing. Increasing. The function is increasing and decreasing. So, also, I would like to point out that some students and instructors like to answer in local maximum, local minimum in the point answer. So input minus 1, that is location of the local maximum, gave me height of 4/3. That is the height of that local mountain. And then input of 1, which is the location of the local minimum, gave me height 0. So the local pit is 0 height. Increasing, decreasing. So where is your hike will be hard, going up, and where is your hike is going down. These questions are very important. Same with your profit. Why the profit of your Amazon production of socks was increasing? Oh, because it was cold from February till March. So that is why it's important to know those things. Derivative is positive, and we're gonna learn soon how do we know that. Where you put a pencil on your graph and your hand is going up, like so. If your hand is going up, then also I can see recently they teach students to have this arrow at the end. So it's keep going up from left. Then derivative there is positive. When, let me put another color, green, your hand is going down, the derivative here is negative. And then it starts going up again forever. The derivative here is positive. As you can see, at the local maximum, local minimums, derivative is not negative and not positive. It is 0 because it's neither increasing nor decreasing. Your hike stops there at maximum and at minimum. You have a break, you breathe, and then you keep hiking. You need to learn how to identify those intervals, writing it in your homework and on a test. The function is increasing. I used green color. the function is increasing from minus infinity to the first local maximum. The function was increasing there. Let's check. Here it is. From minus infinity to minus 1, the function was increasing. Derivative is positive. Then it was decreasing, so I'm gonna need to skip that part. And then it was increasing again from 1 to plus infinity. Notation is important. Do not include those points, because at those points a function is neither increasing nor decreasing. What is notation of union? U. And then from 1 to plus infinity, the function is going up forever. So up, up. That's like how you see it with your pencil. But between minus 1 and 1, in green color, from minus 1 and 1, the function was decreasing. So I will say there, in green, derivative was negative, the function is decreasing. And then I will say these kind of notes. So the function, let me do it like so. The function is, the derivative is negative, the derivative is positive when the function is going, original function is going up. The derivative is negative when the original function is going down. And the derivative is 0. Where? Yes. Look at the graph. Where do you think derivative is 0? At minus 1 and 1. Derivative is a slope. You check the slope here, it's flat. You check the slope here, it's flat. So it's a floor. It's neither increasing nor decreasing. Hike there just stopped. I can see yourself in the camera, myself in the camera over there. That is interesting. Maybe I clicked another button over here. Studio mode. Yeah, it's fine. Let it be. I guess some of the cameras are on. So, just like you said, at x equals minus 1 and x equals 1, the derivative is 0. So not increasing, not decreasing. We have, they call it a relative extreme values. That means something extreme is happening there. What kind of extreme? They mean it's extreme local maximum, local minimums. That's what they mean. These points, since they give you something extreme, they called critical points. And it's going to be one of the most important things we need to teach you, how to locate critical points. Critical points, critical values. I will call them CV. Books in the United States did not agree how to call them. They all agreed to call them critical, but they did not agree to call them critical values, critical numbers, or critical points. So I show all three. That is interesting. In this book, I can see they call them critical values. Well, let's stick to that. Then it's going to be CV. I always make abbreviation consistent with the book. So, critical values, let's call them the definition. Critical values, that is a definition of the function f of x are the x values such that, st is such that two things, either or. Let's do it like so. The derivative is 0, or the derivative does not exist. That is a definition. Let me write it down. Definition. DEF. Definition. So not only local maximum, local minimum can happen where derivative is 0. I'll come back in a second, don't worry. But you know they can happen like over here too. This is also local maximum. But because it's a sharp corner, you remember sharp corners have derivative d and e. We also have to consider that. Sometimes the mountain is just very sharp. So we have to consider both a smooth local maximum or minimum or a sharp one. Both should be considered. See? The derivative here is d and e, d and e. The derivative here is 0. The derivative here is 0. So we have to consider this. This is very important because critical values are candidates for relative extreme values or relative extrema. That is basically local mean and max. That is the same thing. You will see in your book the same, both definitions. Relative extreme values, relative extrema, local minimum, local maximum. That's the same thing. Candidates. They are candidates. I will explain you what it means in a second. The idea is you have a huge long function, a profit of your business for the whole year, for 12 months. It goes up and down and up and down. So you have lots of local minimums and maximums. How will you find them fast? Should you check every single day? No. You find a derivative and see where it is 0 or d and e. Not all of these points will give you hills or pits, and that's why they're called candidates. You only need to check critical values. They're either gonna give you maximum minimums or not, but at least there's nothing else to check. And that's what they call extreme, that's why they call critical. Critical means if there is a top of the mountain, it should be at the critical value. But sometimes that critical number will give you nothing. So that's why they call candidates. Candidates means you have to check. Checked. And checking it means we're going to be, let's not do check. Checking test. Same thing, right? You have to check it or test it. And that's what we're going to teach you. First derivative test and second derivative test. How to test those candidates, which are critical values. Example. Anyway, too much blah blabbing. Let's just do the example and show you. It's always like this. We threw at you lots of definitions, and finally with the example you understand it. You're like, oh, that's what I do. Example 1. With the given function x cubed minus 12x plus 5. With the given function, let's do find CVs. Can you remember that as critical values? Very nice notation. CVs, critical number, CNs. Let's find critical numbers. Huh?
Sorry, I was just going other.
CVs, yeah. Then B, find the increasing and decreasing intervals where the function is increasing or decreasing, going up or going down, right? And then C, find, if any, relative or local max min. They might be none. Maybe it's like a flat curve, but it's a cubic function. Cubic function, actually, you should have some kind of intuition how it looks like. Cubic function have to change direction 3 times. This 3 tells you how many times a polynomial changes direction. 1, 2, 3, either like so, or 1, 2, 3, like so. So one of these. That's like either or. And then like plus 5 is shift up and so on. But this is how it looks like. So I kind of expect to have 2 local extreme values, either maximum and minimum or minimum and maximum. Solution. So this is how you start. Now you have new synonym for the derivative. I gave you derivative synonyms. How fast something is changing, rate of change, instantaneous rate of change, velocity, speed. You know, we asked to take the derivative. And then on the exam you had, what else did we say? Velocity, acceleration of a second derivative, exactly. Marginal for business students. One more new thing now, critical numbers. Critical values, critical numbers. If we ask you to find critical values, it's exactly what you should do. You should find derivative. So now it's one more synonym, because it's exactly the definition. The definition which was here, the definition of critical values is find a derivative. So let's find a derivative, and then I will teach you what to do with that derivative. Now you know how to find derivatives. This is a cubic function, not by definition, thanks God, not by definition anymore. 3x squared minus 12. Agree? Looks good. Good job. Now, when you found it, you need to check where this derivative is 0 and where this derivative is d and e. D and e usually comes from a denominator. So if you ever get a fraction, for example from quotient rule, or derivative of 1 over x, right? You should check denominator. These values will give you d and e solutions. But in this case, you know, it's a polynomial. 3x squared minus 12 cannot have d and e points. It exists everywhere, but it might have 0 points. So they call 0 points zeros, right? And this, you might never hear it after this class, called singular points. Singular. Singular means something bad happened there. That means function derivative does not exist, singular points. So I only do 0 here just because there is no d and e points. Let's do it. Step 2. 3x squared minus 12 equals to 0. Solve for x. 3x squared equals 12. X squared equals 4 divided by 3. X equals 2. Correct? Not correct?
Incorrect. You forgot -2.
Good job. Never forget the -2 part. On the exam, some of you will remember. You're disrespecting -2 if you forget it. Okay, that's just rude. Yes, some kind of panda in zoo cries when you do that. That's a joke, you know, right? Like, don't do that. Don't lose the negative solution. It's important.
Every time you lose the solution, I need to lose it.
Right? Yes. So we have 2. These are in the domain. That's important. Note. There was here, let's see, definition. Actually, it doesn't say that. Okay, then I will show it later. So, these are critical values. Nice. We found 2 critical values. And then, if you want, I can show you ones, but it's kind of a little bit weird to show. 3x squared minus 12 has no d and e points. So we only got critical values from the zeros, not from the d and e points. And we can just divide by saying polynomials are very nice smooth functions. They don't have gaps or asymptotes. Usually these are the d and e points. But when you work with fractions, then you will see also tangent function has d and e points and so on. Yes.
What if there were 3x squared plus 12? Wouldn't that result in an imaginary number as a critical point? Or do we just slow this down?
Good question. If you have no solutions in this class, we will say no solutions. In complex analysis, you will say imaginary solutions. That gives you a completely new world of imaginary numbers.
I was just confused as to what happened in that instance.
Here we say no critical numbers, no hills, no pits.
Pretend those don't exist.
Yeah, we pretend it's fine. Yeah. But of course, imaginary numbers opens the whole world of imaginary world. So that's pretty cool. Now, that was step 2. Step 3. And this is the most important part I will teach you. And usually the way I teach students really like it. So I will teach you how to use a sign line. Sign line. Different instructors teach differently this part, and I'm not taking points if you have your different notation. That is completely fine. I teach it using a sign line. You draw, sometimes they call it a number line, a sign line for the first derivative. That's important. So I'll write down that this is, let me move it a little bit lower. Here. It's just easy. Okay. This is the first derivative, bless you, sine line. Now, let's see what is happening here. You should put your critical values on the sine line. We have 2 minus 2 and 2. Here it is. Put them in a normal order, so not 2 minus 2. Minus 2 and 2. Then we want to find what is happening around minus 2 and 2. Because we know that here and here, derivative is 0. But now we want to check what is happening before and after. Because the definition of a local maximum says it's maximum if this is the biggest local point, or it's minimum if it's the lowest local point. And this is how we're going to do that. We will be using test points. Test points. To check the sign of the whole interval. Test points are very random, and that's why your homework will be different from other people's homework, and your exam will be different, because it's just very fine with your imagination. Choose any random point on the whole interval. For example, interval number 1 is this interval that goes from minus infinity to minus 2. Choose some random point, and you think that it belongs there. That's what it's called a test point. I like choosing minus millions because I like huge numbers. They make kind of good feeling of what is happening. But students like to do 10, minus 10, 0, 1, minus 1. Which kind of you prefer for this interval? Which one?
Simplicity. So probably we want to choose ones that are easy to calculate.
Make a choice, people.
Minus 3.
Minus 3, yeah, why not? Minus 3. I like tens because they're easy to calculate. Minus 3 is a small. Don't choose fractions, that would be weird. Minus 2.7, like you make your life harder. So, test points are only need for testing. That's why it's not important which one you choose. You just have to be on that interval. F of minus 3, not f, the derivative. So remember, the sine line is about derivative. You want to check if derivative is positive or negative at that interval. So now you will plug it into your derivative. Let me make a note. Plug into your f prime derivative. That's important. So I'm going back, and that is why it's good habit. The moment you found your derivative, put it in the box because you will be reusing it. And then second derivative will be important soon. Also put it in the box. My derivative is 3x squared minus 12. So I'm plugging 3x squared minus 12. The thing is, I don't need a number as the answer. I just need to know, is my derivative positive or my derivative is negative? And that's a good part of it. I don't like calculating numbers. It's just too slow. That's why I like to use a million. Million minus million. Minus million squared times 3 definitely is bigger than 12. So that should be positive. Do you know what I mean? You just need to have a feeling about the sign. How about here? 3 times 3 with negative is 9. 9 times 3 definitely is larger than 12. So the answer is positive. And this is the first time probably in math you see that mathematics is not about numbers as you might believe before. Mathematics is about understanding concepts and why they are important. I really don't care what's the answer of this number. I just need to know the sign because that is important concept. Wherever since, and it's the only time I will write this down, so carefully, since derivative at minus 3 is positive, then the original function is, what do you think?
It's
Increasing on that interval I chose. So this is my notation. This is how I teach. Not all instructors like the way I teach it, but students like it a lot. The f is increasing from the left up until minus 2. Why? Because in blue color, the first derivative is positive here. So red color is original function. I'll put it, yeah. Sine line belongs to the derivative. Test point belongs to the derivative. We plug test point into derivative. But the conclusion we need is about the original function. It's going up. The hike is going up. That was the first test point. Second test point should go into the second interval. From -2 to 2, what kind of convenient number you want to choose?
0.
Good choice. Definitely. Don't choose something like 2.
Square root of 2.
0, square root, yeah. That's nice
Square root
to...
of 2 would be pretty easy.
0 is good. 0 is a favorite number to choose. Let's plug 0. So I'm plugging really fast. It's 0 minus 12. Positive or negative? Negative. And again, since f prime of 0 is negative, that's the only thing I need, then the original function is decreasing. And this is the notation I teach. I put in blue color minus. Colors, that's your choices. You don't have to use it. And then in red color, it's going down over here. Going down. This is a very visual picture because some teachers force you to memorize. If the original function was going from, if the derivative changed from plus to minus, it's maximum. This is hard. I don't like memorization. Visually, you see this is the top of the mountain, right? So this is local maximum. Nice. And that's why I like this notation a lot, because visually you don't have to memorize it. From plus to minus, increasing, decreasing, what is that? Top of the mountain, that is local maximum. Let's check the last one. F prime of. Last interval is from 2 to plus infinity. Choose test point.
3.
I would choose 3, but 10 also good. Why not?
Because 3 is less than 3 feet our work.
I like the idea of 3 because since it's squared, the answer will be the same. 3 squared minus 12, we already know it is positive. But I usually actually choose 10 and minus 10. I like this a lot. Positive, blah, blah, blah. Derivative at 3 is positive. Then f is increasing. So what happened here, almost done, just a second. I'm gonna put plus, and then with a red color, I'm going up. So visually, you can see this is a pit of the mountain, or a valley, right? So it's local minimum. And that's how you avoid memorization, because sometimes they give you a table from plus to minus is maximum, from minus to plus is minimum. No, visually, it's nicer to see it. Okay, ask me. What do you think?
Do I have to show my testing points, or can I just do it in my head?
You should show. On the test specifically, we'll ask you to show the work, yeah. Or else, again, I always say, you have to understand how would you prove to me that you did not look at your neighbor's work and copy it. That's how. Especially with test points, it's so random that I should see you did it. Yeah, you did it yourself, I mean.
Random log over plus test points.
Yeah, because again, I like to choose minus million plus million, because when I plug a million into here, it's very visual. Million squared times 3 definitely is positive. So, yeah, I really like using huge numbers.
I have a lot of early squares memorized, so it's not a problem for me.
So why did we do that? What was the first question? I didn't remember. Let's see. The first question was A, find critical values. And then B, find where it's increasing, decreasing. And C, locate relative maximum and minimum. We just did all of the work. All of the work is done. So answer. Let's just think. We did everything, now we can answer. A, the critical values where? Critical values. Since they're called values, which is a synonym of inputs, those are only x numbers. -2 and 2, exactly. B, where the function is increasing and where the function is decreasing, interval notation. So original function is increasing and decreasing. I always do the shortcut. Incur, decur, very smart. Okay, this is hard because you don't have a graph, but you have this sign line I just taught you, and that's the best way to see it. Where is your function increasing? Yes, I can hear from negative infinity to -2, and then it was decreasing, but after this, union from 2 to plus infinity. 2 to plus infinity. Two ways to understand how we got this. Either way, your derivative is positive. Derivative was positive here and here. These were test points. Locate which intervals this test point belonged. Here, 3 here. So from minus infinity to minus 2, my hand goes up. And then from 2 to plus infinity, my hand goes up, increasing. Between, it was decreasing. What is between minus 2 and 2? Do not include endpoints. At endpoints, you have critical values, not increasing and not decreasing. C, find any relative maximum and minimum. So, relative or local maximum is happening, and then let's do relative or local minimum is happening at x equals. We have two critical values, and both of them gave me actually some important information. Minus 2 gave me which one? Maximum, because it's on top of the mountain on the sketch. That is not the graph of the function, that was a sketch of the function. So at negative 2 I have max, and at 2 I have mean. But we also, as the scientists, need to know how high the function went and how low the function went. So your profit has minimum in July. Well, how low it is? Is it that bad or just not that bad? So we need to find f at minus 2 and f at 2. That is plug into original. This is always the same step at the very end. We want to know how high or how low my maximum and minimum goes. The original function, I don't even remember how it looks like, but I can go and check. F is x cubed minus 12x plus 5. So I'm plugging in there minus 2 cubed, minus will matter this time. Minus 12 times minus 2, put parentheses, that's important, plus 5. Same thing here, 2 cubed minus 12 times 2 plus 5. So the top of the mountain, the maximum, was 21 units high. The minimum was 11 units low. That is the idea. Thus, when you make a sketch of the function, and now we know how the cubic function looks like, f of x equals x cubed minus 12x plus 5 was going up, reaches the local maximum, going down, reaches the local minimum, and going up. Local maximum has the location minus 2, 21. Local minimum has the location 2, 11. That's exactly how cubic function looks like. So it's exactly what I predicted, as I told you before. Goes either up, up, or down, up, down. And we finished only one problem. So you can imagine your homework will be time consuming. I know. This is a perfect free response question on exam 2. This is what we put on a free response question.
On the homework for
Just a second.